All right, so while people are trickling in, let me start slowly by reminding you some of the things we said last lecture. So we were talking about the basic introduction to effective field theory. So I told you about a whole bunch of reasons and motivations for using effective field theory. And then we sort of boiled down to the fundamental ingredients of any effective field theory, which are what are its degrees of freedom, what fields is it built out of, what are the symmetries of the effective theory, which could be approximate symmetries, exact symmetries, spontaneously broken symmetries. What is the power counting in the effective theory? What are we expanding in? What are we neglecting at leading order? Then we talked also in the context of power counting about the fact that many times in a Lorentz invariant context, the power counting is simply given by the operator dimension. And so that's very simple. We just look for higher dimension operators, and we know that they're subleading to the operators of lowest dimension. The operators of lowest dimension are going to dominate the dynamics. When we were talking about that, we also talked a little afterwards about this concept of field redefinition. What are the coordinates of the field theory? And so there's a freedom to pick those coordinates, and that freedom can be used to simplify the basis of operators, in particular the basis of subleading operators can be simplified. And after making field redefinitions, we can get to a minimal set of operators. Now, with that minimal set of operators, you may still make field redefinitions. It's up to you at that point. And so you still may, work with a different set of fields than your friend, but that's then just a choice of coordinates, if you like, on the effective field theory. How do I pick those coordinates to do my effective field theory? Yeah. 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 Yeah, I mean, you could still make a field redefinition in a non-effective field theory context, right? But then the terms you induce from that functional determinant would be terms that you would have to keep, right? So you'd have some additional Feynman rules associated to them. Then you would just be really making coordinate changes in your field theory, and that's fine. You can always do that. The question is it helping you? And it's helping you in the effective field theory context because you can make an expansion, and the higher order terms that you're inducing are terms that then you can neglect. Yeah. We talked about a kind of important example in particular for particle theorists, and that's the standard model is an effective field theory, otherwise known as SMEFT. And in this effective field theory, the power counting is just in terms of the dimensions of the operators. You're expanding in standard model scales that I called MSM, and you're saying there's some new physics scale that's much higher. There's a gap. There's no particles up to that new physics scale, and we can make an expansion in this way. We can organize the effective field theory in terms of standard model fields, and we can write down higher dimension operators built out of the standard model fields that are Lorentz invariant because we choose not to break Lorentz invariant, that are gauge invariant because we choose not to break the standard model gauge group by these higher dimension operators. And then we can just categorize them and write down a complete basis. We use field redefinitions to remove so-called redundant operators using this. In the case of dimension 5, not counting flavor, there's only one operator. In the case of dimension 6, not counting flavor indices, there's 59. And we started talking about some examples of these operators last time. So I want to just start today's lecture by another example. So we talked about the dimension 5, which is giving rise to a Majorana mass term. We talked about one example of dimension 6, which would contribute to G minus 2 of the muon. And so let me give you one more example. So let me give you a more collider physics type example. So say you were interested in Higgs to gamma gamma, which you have already talked about. From the standard model, the usual standard model, if we calculate this process, it occurs at loop level. Okay, there's not a tree level coupling of the Higgs to the photon because Higgs couples according to mass, and the photon, of course, is massless. So to get this process, you're going to have diagrams of the Higgs, and you got to couple to something massive, which, okay, the heaviest thing is the top quark, so Higgs like to couple to the top quark. And of course, the top quark is charged, so it can emit photons. So you would have a diagram like this one. And another heavy particle that the Higgs likes to couple to is the W, also charged, so it couples to photons. So we have a diagram like this as well. And so there's some suppression by this. In some units, it's 2 parts in 100, 0.02. Some loop level suppression from the fact that the diagrams are in the standard model. The usual lowest order, dimension 4 or less standard model, are loop diagrams. So this is just, I haven't told you how I normalize, so telling you it's 0.02 is not really that meaningful, but gives you a sense of the type of suppression. Now we can look at these operators here. In L1, there's no operator that would mediate this process of Higgs to gamma gamma, but if we go through this basis of 59 terms, then there are dimension 6 operators that can mediate this process. So I'll show you a couple of them. We need a Higgs field. We need a photon field. Remember that the photon field lives inside 2 different field strengths. We have 2 photons, so we need 2 field strengths. We can write down an operator like this. The W mu A is the one for the SU2 left, and we have an analogous one for the U1 of hypercharge. And it turns out that this isn't a complete set. There's 6 operators total. I just decided to write 2 of them. If you look through the basis of operators that's in the online course, you'll see that there are some other examples as well. And these operators mediate the Higgs to gamma gamma process at tree level. So we can have a Feynman diagram that gives us a Feynman rule from these operators that just has a single Higgs coming in and 2 photons going out, and one of the Higgs is replaced by a VEV. So there's kind of a factor of V. So 1H goes to V effectively, or more accurately, 0V since it's doublet. And the other Higgs is just dynamical, and we could take the field portion out of it, and then we have this process. So we have a tree level process with coefficients of these operators, all 6 of them, that competes with a loop level process. And I decided not to go through the numbers for this, but you can go through the numbers. It's better to write down all 6 operators because some of them have opposite parity and don't interfere with these, only interfere with themselves. So there's some subtleties when you go through the whole analysis. But the interesting point here is that you can have loop level standard model processes from L0, the usual standard model, competing with these higher dimension operators at tree level, and that means that there's going to be sort of, if I don't see any kind of deviations from the standard model, even further suppression of these operators, or it gives an opportunity. And if we're looking for new physics, if we have loop level here, we have more chance of finding new physics that could be encoded by these operators. So sort of a general strategy is to look for things that with L0 don't happen. There's also baryon number violating operators at dimension 6. It's another example, something that doesn't happen with L0, and that's also something that is important. Of course, those operators are very highly suppressed. We haven't seen a proton decay. Okay, so this is the end of my discussion of the standard models and effective field theory. We may come back to it, but I'm going to change gears. So if anyone has a question about this, I'll take that now, and then I'll switch to giving you some other examples, kind of completely different examples of use of effective field theory. All right. Well, let's ask a question that's maybe particularly important today, and that is, let's ask the question, why is the sky usually, not today, blue? Now that seems like a very different question than the things that we should be studying in this course, But this is a question that we can answer with effective field theory. All right, so we're effective field theorists. We want to answer this question. And so we say, okay, it must have something to do with photons that are coming into our eyes, and they're coming from the sun. So but why are we seeing the sky being blue? Well, we're seeing the entire sky be blue, and so there's got to be some scattering process. Scattering. That's a question for a particle physicist. So there's going to be scattering of photons by the atmosphere. The atmosphere is made up of a bunch of neutral atoms or molecules. It doesn't really matter for the description I'm giving, whether they're atoms or molecules. And they're in their ground state. So there's nothing to do with de-excitation or anything like that. It's just photons from the sun are scattering off the atoms or molecules in the atmosphere. Okay, and it's low energy relative to the scales in the problem. So let me define what I mean by that. So we have the energy associated, the energy of light, what we can see with our eyes. And that is much less than the typical excitation energies of atoms, which go like, as we talked about last time, the mass of the electron times alpha squared. This is like the Bohr transitions. And that is going to be much less than the typical atomic size, which in units of an energy is ME. So A0 would be atomic size, dimensions of length are 1 over dimensions of energy in particle physics units. And as an energy, it's mass of the electron times alpha. And that, again, is much smaller than the mass of the atom or molecule. So we have a hierarchy of scales here, and we're interested in the smallest one. So we should be able to use effective field theory. Okay, well, scratch our heads. We need photons when we need atoms. So it's sort of clear from the description of the problem. So let's start by talking about the degrees of freedom associated to the atoms. The atoms are very heavy. They're like the proton in our description of hydrogen. I said when we take the mass of the proton to infinity, it's like the hydrogen just acts like a static source of charge. We choose to make it sit at the origin. So the atoms are like that. They're very heavy. And we can describe them. We want to sort of think about fields for the atoms. So we can describe them by some particle that just sits in one location. Well, it still exists for all time. So if it sits in one location, I stick it there, and it just propagates, it stays there for all time, then the only kind of evolution it has in the Lagrangian is a time derivative. Okay, no spatial derivative, just a time derivative. So I put in I partial 0. Now, I partial 0 is not something that is Lorentz invariant, right? Which sort of picks out a special frame, but that's okay. Not a problem. We often like to write this like in a little bit more covariant way. And that's kind of useful when you're building higher dimension operators. So let me define something that just picks out the time component. It's a vector v, 1, 0, 0, 0, and v dot partial is just the time derivative. Okay, that's just establishing some notation. So this phi v destroys an atom. Phi v dagger creates an atom. And if I ask about the mass dimensions of phi v, well, I just look at the Lagrangian. This partial derivative has dimension 1. The action should be dimensionless. The measure, mass dimension minus 4. So the phi v kind of looks like a fermion in this sense because there's a single derivative. So phi v has dimensions 3/2 in 4 dimensions. Even if it's a boson, it's 3/2. If little d is equal to 4 for 4-dimensional theory. So fermion, boson, 3/2, just the sort of, by taking this limit of the static, it just becomes a field of dimension 3/2. There's some factors of m that come in the appropriate way to make it 3/2 if you go from some relativistic description. What kind of symmetries do we have in this problem? Yep. Yeah, so a total time derivative I can remove just because it would be a total derivative of the whole field, and then it would give me a spatial, okay, an integral at time equals infinity that I'm dropping. So I don't need a total derivative of something. And then I could always integrate by parts and put the time derivative on phi dagger. And if I want to show that this Lagrangian is Hermitian, I indeed, if I take the Hermitian conjugate, it'll end up that way, right? And I can integrate by parts because of what I told you, that the total time derivative, so it's going to give back this operator. Ah, right. So if we put a second derivative, then of course we're going to get something of higher dimension. And so we're going to be, in this effective field theory, we're going to be counting dimension, just like we did last time. And so this is the lowest dimension operator that I can write down that does what I want. Good questions. Okay, what kind of symmetries are we going to have? Well, there's going to be photons, and so we should have a gauge symmetry for the photons. Usual gauge invariance, U1 electromagnetism. There's no reason to think that parity or charge conjugation would be violated or be anything related to that. So we will impose those as symmetries. And those are going to constrain the interactions that I can write down. Okay, we have PCT, so time reversal is also going to be fine. So let's think about, this is very limited. I don't want to write down the whole theory. I just want to answer this one question, right? So let's think about the terms that are in the effective field theory that would be ones I want for answering this question. So those are some interactions of this atoms with photons. Well, the atoms are neutral, so I can't have a covariant derivative on the atom. There's no charge for the atom. So maybe before I write this, note, atom's neutral. So if you like, if you want to say it formally, that this is just the partial derivative. There's no photon. The photon term gets dropped because the Q in the covariant derivative that tells you the charge of the phi is 0, so you just get the partial derivative. So covariant derivatives are not going to be so useful, but we still have F mu nu. And so we can couple atoms with F mu nu. And because of charge conjugation, we actually need two Fs. If you use charge conjugation on F, it goes to minus F. And so we need two Fs, not just one. The phi's are charge conjugation even. And so we could write down an operator that looks like that. Because of the availability of V, it turns out that there's a second operator we could write down that couples atoms and photons. So I could just invoke some V's, and I can get an operator that looks like this that also works, picking out some time components of the photon. So both of these are good operators for this problem. And the F is antisymmetric, so I can't dot two V's into it, only one. If I dotted two, I'd be dotting in something symmetric, something antisymmetric. So that, you can go through and think about other possibilities, and we arrive at these two. So let me just write even numbers of F's due to charge conjugation, which I'll just denote by C. We could also think about equations of motion that would tell us things like this, or things like this. We didn't really need those, but they're there if we need them. And so we end up with these two operators. I also didn't write down F mu nu dual, an epsilon tensor dotted into F, and that's because of the parity If I had something like F dual, that would be parity odd, and I assumed that parity wasn't broken by these operators, so no FF dual. Okay, so then we can just look at these operators. What do they do? Well, there's an atom, and then there's some coupling, and it couples to photons. So it has some interaction like this, right? So it allows photons to scatter just directly by this operator off of an atom. Okay, so it seems like we should be able to answer the question maybe we set out to do with just this operator. At least it's describing the process. So power counting is in dimensions. There's nothing too subtle here, so this is the case. And so we have to ask, what are the dimensions of the taus? Well, the tau 1, the V is dimensionless, so the tau 1 and the tau 2 have the same dimensions. So what are the mass dimensions of these taus? Who's awake this morning? It gives me time to drink. Yep. Good. So mass dimension is -3. We're 1 over lambda cubed for these taus. Some scale. So we have to sort of ask, what is the right scale there? So if we think about what's going on in the process, the low energy photons aren't probing inside the atom. They're just sort of glancing off the atom. The dynamics inside the atom, which is all the energy levels, etc., is something the photons are not seeing. And so we might expect, and it's a reasonable choice, that the cross-section size is set by the atomic size, A0. So that's a high scale here. So tau 1 is of order tau 2, and it's of order mass dimension to the -3. A0 is a length, it's the Bohr radius, and so A0 cubed is mass dimension -3. And that's a large scale, or small length scale. Okay, so now we can think about trying to answer the question. Seems like we maybe have to do a little bit more, but I claim that we can already think about answering the question. And that is because dimensional analysis is a very powerful tool. And that's the reason I gave you this example. So the cross-section has dimension -2. The cross-section is proportional to the amplitude squared times some phase space for the scattering. And in general, we have to work out what the phase space is for the 2 to 2, for the scattering of 2 to 2. Photon and atom go to photon and atom. But what do we know? Well, just from dimensions, we know that the A goes like A0 cubed. And that means the A squared is going to go like A0 to the 6th. Okay, just by tracking the A0s. And therefore, the cross-section is going to be proportional to A0 to the 6. And then we just, okay, the phase space and the rest of the dimensions just have to be made up by some dimensions in the low energy effective theory. And the photons are on shell, and the photon energy is the sort of thing that's relevant because the atoms, you know, they're just static. There's no scale associated to their Lagrangian. And so the relevant thing in the scattering process is the energy of the photon. And we can just stick in the right number of e's to get dimension -2. So that's e gamma to the 4th. Okay, maybe there's some angles and stuff, but we don't worry about that for just making this little argument. And what does this little argument say? Well, it says that things of higher energy scatter stronger than things of lower energy. And blue light, which has smaller wavelength, has larger energy, because wavelength and energy are inversely proportional. So blue light scatters more strongly than red light and other parts of the visible spectrum. And that's why the sky is blue. Because the photons that are blue are the ones that are scattering. They're scattering into our eyes. The photons that are the other colors, like red, okay, they're just coming through the atmosphere. And we still see sort of the sun is mostly white, but the blue light is getting scattered. And that's why we're seeing blue light scattering around in the atmosphere coming to us eventually. Yep. Ah, very good question. Why is the sky not violet? Because violet has a smaller wavelength. And it turns out that, okay, that's a more detailed question. So the sky is not violet because actually the upper atmosphere absorbs a lot of the violet. Yeah. Also, your eyes are a little bit less sensitive to violet than blue. That also has some impact. And to analyze those questions would require more detailed study of the effective field theory than I want to go into today. But it's a good question. All right. Any other questions? So this is a very powerful tool. You see that we can sort of very quickly get an estimate for the size of a cross-section just by some simple dimensional analysis. And it turns out, I'm going to emphasize this point by giving you a few more examples, that as field theorists, as particle physicists, or many types of physicists, you could be a condensed matter physicist, you could be an astrophysicist, dimensional analysis is your friend. And so even if you're a model builder, you're building models of new physics, you're not trying to describe some process that we know exists, but you're just trying to describe some processes that we don't know exist, or some contributions to processes that we don't know exist. This type of estimate is very useful. Say you were to build a model for new physics, and you want to know kind of quickly whether your model is okay or not. You could do something like this, and very quickly figure out, are you within the bounds, or are you going to be order of magnitude too big, in which case, find another model. Or are you going to be order of magnitude too small, and it's just going to be impossible to see your model, then maybe you're also not interested. So you can quickly figure out kind of are you in some interesting range just by arguments like this one. So let me give you another example, kind of a classic example of effective field theory. Let's consider photon scattering at very low energies. Okay, well you say, how can that be? I'm thinking about photons scattering on photons. But photons, of course, are not charged, so there's not like a gluon where I have a 4-gluon interaction. The photons, there's no full 4-photon interaction. So, how can this even happen? Well, of course, the photons do couple to electrons. So in QED, or in the standard model, we have a diagram like this one with an electron going around. So photons can scatter on photons through this loop effect. Now, if I'm at very low energies, I can integrate out the electron. The electron can be heavy compared to the photon energies that I'm interested in. So let's construct that effective field theory. Well, the lowest order term in this effective field theory is just the photon gauge term, or kinetic term. Not gauge, but. So we just have F mu nu, F mu nu. Okay, we could add some gauge fixing if needed, but let me not do that. And then we want to add some interaction that allows the photons to scatter that's sort of related to this diagram. Since I already kind of know where it's coming from, I'm going to make use of that a little bit, just in how I normalize my interaction. So if I look at this diagram, there's a power of the coupling at each of the vertices. So it's giving an e to the fourth. If I know something about how loops work, there's always factors of 4 pi. In this case, 16 pi squared, 4 pi squared. So this is actually alpha squared. So let me, my interaction here, already stick in an alpha squared. If you like, it's just a way of normalizing my subleading operator. And then I have to think about what type of operators I can write down. Well, I really only have F. The electron is gone. E gamma is much less than the electron. The electron is a high scale. I don't write down the electron as a degree of freedom. The only degree of freedom is the photon. And so what I can write down are things involving F. Charge conjugation is again obeyed. I don't have 3 Fs, but I can have 4 Fs. So I could have a term like this where the Fs are contracted and I square it. I could also take an F and an F dual and square that because I have 2 F duals. Parity is going to be fine. And this is an independent operator. I can look at the dimensions of these. F is dimension 2. I have 4 of them, so this is dimension 8. And so to get something of dimension 4, I normalize. My coefficient here is me to the fourth. Now the C's are dimensionless, right? So I've pulled out the dimensions. See, these are dimensionless. Just by sort of construction. So those are some dimensionless coefficients. You might think maybe they're order 1, or maybe they're order some loop factor. This is the lowest order theory, and there's 4 Fs. 4 Fs is going to do exactly this, scatter the photons. So this is known as the Euler-Heisenberg Lagrangian, and you could go, of course, beyond the dimension 8 if you wanted to. And it gives a 4-point function, 4-point interaction that does exactly what we want, allows photons to scatter. Okay, well, let's do a little dimensional analysis. We could do more with this Lagrangian, but let's do a little dimensional analysis. If I look at the amplitude that comes from this Feynman diagram, it just has alpha squared over me to the 4. And then I can think about the dimensions of the amplitude. Okay, well, a little known fact, which is useful to know, is that the dimensions of an amplitude are 4 minus the number of external particles in our usual normalization in quantum field theory with relativistic normalization. You're basically subtracting 1 for each external particle because in the states, in relativistically normalized states, whether it's a photon state or electron state, whatever the state is, it's always dimension minus 1. That's the usual convention for relativistically normalized states. And so the amplitudes are going to be 4 minus the number of external particles. There's 4 external particles, so the amplitude should be dimensionless. If I had 5 external particles, it should be dimension minus 1, etc. So I can do some dimensional analysis and say, oh, the extra thing that can show up here is some frequency or energy. Let me call it energy, since that's what we called it over there. Some energy to the 4th. Now the exact details, I put a little twiddly. There's 4 photons here. Is it this photon energy or this one? Is it this one dot this one? Those details are important, and this Lagrangian allows you to figure that out, but I'm not worrying about those details here in lecture. We could figure out exactly what the Feynman rule was, right, from this Lagrangian and write this down. This is just a dimensional analysis, so I just wrote E gamma to the 4th. All the E gammas of all the photons are similar in size. So I'm using some kind of estimate that there's just some common E gamma rather than tracking the individual E gammas. Okay, and then we could do the same exercise we did over there. cross-section is amplitude squared times phase space, okay, which could be an equality. And then I can just stick in this estimate. So I get alpha to the 4, me to the 8 from squaring the amplitude. I get an e gamma to the 8, but the cross-section has to have dimension of -2, so I need an e gamma squared downstairs from the phase space. So putting things together, I have alpha to the 4, me to the 8, e gamma to the 6. Okay, so it's a pretty strong power of e gamma for any e gammas much less than me. There's a lot of suppression from e gammas over me. Remember, e gamma over me is a small number. So this is a small process. You could contrast that if, for example, you didn't know anything about QED, like imagine we were in the dark ages before Maxwell, but we still knew some field theory. Imagine that. And you might say, oh, well, maybe it's a scalar. And we don't know about gauge symmetry. And then you might write down something like that was phi cubed, phi to the 4. And you see that the dimensions of this thing are being affected by the fact that f has dimension 2. A scalar with phi would have dimension 1, right? And the fact that you're getting a lot of the suppression of those powers of me downstairs is coming from the fact of the gauge symmetry, right? Needing to use the f. And so if you had something that was like a scalar, you would not have the suppression. And this thing could be orders of magnitude bigger if it was not. So like the dynamics of the theory are really predicting this thing is small. And it's coming about from the fact that photons are of gauge symmetry. Okay, this theory, of course, we thought about it like with these C's as if they were just some order 1 numbers, but we could calculate them, right? We just do this Feynman diagram, expand at low energy, and it tells us the C's. This is a procedure called matching. We look at the theory QED, which is the mother theory of this low energy effective theory. And we do a calculation in that theory to determine the coefficients of the low energy effective theory. Okay, if we do that, it turns out that C1 is 1 over 90, and C2 is 7 over 360. Some numbers, they actually further suppress the cross-section. And we could, do the exact calculation, which I looked up. There's a 1 over 16 pi from the phase space of 2 to 2 scattering, and then there's these numbers which come together in some way that gives a funny number, but it's an order 1 number. It's like 1.5-ish. Okay, so there's the exact formula. If you do more details and calculations, you know the C's, you do all the phase space integrals, put in all the factors of 2, then this is what you get. This part, which is the only sort of thing that's causing suppression, we could also estimate, because this is actually generic, and it's from the phase space for 2 to 2 scattering. So we could actually have put that in if we knew a little bit about how cross-sections work. Okay. But we get pretty good estimate just with our dimensional analysis. Now, I didn't put the angular part in, so maybe the equals is in quotes, but yeah, maybe we integrated over the angles. I think that's what this formula is actually for. So it's the total cross-section, not the differential cross-section and angle, which we could also compute. Okay, so just kind of rapid fire, just like, okay, we know this idea, we could sort of extend it and think about other things. So like we could think about, what if they were fermions? We could have four different fermions. Maybe they have different identities, so I call them phi 1, phi 2, phi 3, phi 4. And so quickly, that would be some operator with some heavy mass suppression, so something like this. Let me call it lambda. This is dimension 6, has to be suppressed by 2 powers. Okay, what's the amplitude goes like 1 over lambda to the 4. Cross-section, the cross-section goes like amplitude squared. Amplitude squared gives me a lambda to the 4. Cross-section has to be dimension 2. So there's going to be some energy scale. So we can just kind of keep doing this kind of exercise, right? And we see for this process, it would be energy squared for energy much less than lambda. We could also, with this process, do sort of a decay rate. Let's imagine that these masses of these things are all comparable, but one is heavier. So one can decay to 2, 3, and 4. And then we could calculate a decay rate. And again, there's a 1 over lambda to the 4. And now the decay rate has units of energy. And so there has to be some energy scale. I could put energy, but since the mass, I said this has some mass. So M1 is bigger than M2, 3, 4. So M1 is the biggest sort of scale, so I can think of that the decay rate goes like the mass to the 5th. And this is actually what you saw in the lecture yesterday, not my lecture, but about the decay rate of the muon, right? It went like G Fermi squared times mass to the 5th. It's a 4 fermion operator. There's a dimensional analysis that gets you that. Okay, etc. We could do fermion scalar goes to fermion scalar. So now the dimensions are less because scalars have less dimensions. So we only need 1 over lambda. And now the cross-section goes like 1 over lambda squared from just squaring the amplitude. And we don't need any additional factors of energy. So we can get a constant cross-section from this process. Okay. So hopefully I've beat on that use of dimensional analysis enough that it sticks. But it's a very powerful thing. And then, of course, we can go into the details and but it's better to do this first, right? To figure out how big something is, get an idea, and then go and do the details of the Feynman diagram, keeping track of all the indices and factors of 2 and signs, etc. Something came up in this example that we talked about over here, and that was this idea of matching. So I'd like to talk a little bit about that generically. And that brings me to the topic of how people talk about effective theories. And there's 2 different ways that are sometimes used. And that they go by the names of top-down effective field theory and bottom-up effective field theory. So let me contrast these 2 and define them for you. So we'll start with top-down. So the idea of the top-down effective field theory is that we have 2 theories. I'll call them theory 1 and theory 2, just to be generic. Theory 1 contains the physics of theory 2. It's the mother theory to theory 2. Maybe theory 1 is QED, and theory 2 was this Euler-Heisenberg Lagrangian, as one example. So theory 1 could be good enough. We could do the calculations in theory 1, but we're not really satisfied with theory 1. Maybe it's a little too complicated. If someone told me the coefficients, doing the calculation from this effective theory is much quicker than doing the full box integral. And actually doing the box integral and the limit that the photon energies are very small is a lot easier than doing it exactly with exact energy over mass of the electron. So we like theory 2 because it's giving a simpler way of calculating. So in this case, the high energy theory is understood. So the high energy theory is theory 1. But we want a simpler theory, and that is theory 2. And the fact that there's an arrow between them is because I can use theory 1 to construct theory 2. And so there's some terminology that sort of goes along with that. I've used a little bit of this terminology already. We can say we integrate out the degrees of theory 1 that aren't the relevant, that are very far off shell, very heavy. We integrate out those things. We remove the heavy or off shell degrees of freedom in theory 1. I'll just call them particles. And by doing that, we can typically do that procedure perturbatively in quantum field theory sense. And by doing that perturbatively, we can match this language that's used onto theory 2. And when we do this matching in this kind of procedure, theory 1, because we have sort of total knowledge of theory 1, we can both kind of get the operators from the matching, construct them from our knowledge of theory 1, as well as the coefficients. So theory 1 is sort of providing us with handle to construct the effective field theory. We just take the full theory. It's kind of like we do a Taylor series expansion of this theory 1, which is often called the full theory, or the mother theory, but usually people call it the full theory. We could call it the father theory or the mother theory, but let's call it the full theory. We can use our handle on that theory to get at theory 2, and it's a very powerful tool. It's kind of like doing a Taylor series of theory 1, which is the high energy theory, and we match that onto the low energy theory, which has some sum of operators of increasing dimension, maybe, that looks like this, schematically. So construct operators and calculate coefficients, which we just talked about in the case of the Euler-Heisenberg, the C's. We just calculate them numerically. All the couplings of the low energy theory we can calculate from the high energy theory. And the technical description of how that exactly works in the quantum field theory I'm going to come to, well, likely next lecture. That's the plan. So we'll leave that beside. But at tree level, it's kind of easy to understand. We just do the Feynman diagram, expand, we get an answer. We call them the values that we get the coefficients. At loop level, there's some more subtleties, and those are the things that I will get into in the next lecture. So this is the idea of using a top-down effective theory. This is at the top. We can use it to get down to the lower energy theory, theory 2. Now, one important fact about these theories is that the reason that this whole procedure works is those theories describe the infrared physics that we want to study in the same way. They agree on the infrared physics. The infrared physics is the physics that's in the effective field theory. That's the physics of the fields in the effective field theory. That's the low energy physics. So we say that the two theories agree about the low energy dynamics. Of course, that means that they could differ somewhere, and they differ about the high energy or ultraviolet physics. And that's fine. That's the physics that we're integrating out. The heavy particles, they describe them differently. Okay, they're gone from the low energy theory. They're still dynamical in the high energy theory. So it's obvious that the ultraviolet physics should differ. But it kind of goes further than that. Even the sort of divergence structure of the two theories differ. If I sort of think about loop level, So the divergences in the low energy theory and the high energy theory, those are coming from the ultraviolet. Those aren't going to agree. We'll see how this all works next time. Okay, so that's top-down effective field theory. What's bottom-up? Oh, maybe there's one more comment that I should make here. Let me use some other color. So what exactly theory 2 is depends on the problem you're trying to solve. We saw sort of a bunch of examples, the different effective Lagrangians. So the path arrow here depends on what kind of problem you're trying to solve. This theory actually might describe many more problems than this theory. This theory is tailored, designed for a particular problem to be the simplest framework for that problem. Theory 1, if we're interested in a different path, there could be some other theory 2 prime that's the right theory to describe that problem, and it could also be a descendant from theory 1. So theory 1 has multiple children, if you like. And if you think about theories like QED or QCD, in QCD, there's like tons of these arrows. People use all sorts of different effective theories to describe various limits of QCD, whether it's high density, high temperature, heavy quark, etc. Chiral perturbation theory, soft linear effective theory, heavy quark effective theory, the list goes on and on. So there's lots of descendants from QCD down these arrows, and it's typically the case that if you have a sort of a full theory, there's different paths you might take. Okay, so what's bottom up? So in bottom up, we might think that there's some theory 1, but we don't know it. So I put a little dash box. And nevertheless, we can still construct an effective field theory to describe a problem, namely theory 2. So maybe there is some underlying theory, but it's unknown to us, often the case. Or it could be the case that the matching procedure that I outlined is very difficult, and we just don't want to carry it out, or maybe we don't know how to carry it out. Maybe it's a non-perturbative calculation, so we can't carry it out, at least on the blackboard or pen and paper. In all those cases, we can still make progress using this notion of effective field theory. And in fact, many of the examples I've given you are exactly of this type, where we just started with this theory without really referring to the full theory. So what are the procedure here? Here we really rely much more on the symmetries. We don't have the high energy theory as a crux, but we can still just use our powers of effective field theory, the power counting, the symmetries. We can just write down complete bases of operators at a given order in the power counting. And that's how we construct the sum of low energy operators in some power counting expansion. So we just write down the most general set of operators that are consistent with the symmetries. And power counting. And of course, we know what fields we're using because we know the degrees of freedom. So it's the same procedure that I've been emphasizing. But we don't have the full theory to do calculations to determine them, so we just sort of have to go from the bottom up, just writing them down. In this case, the coefficients of the operators are something that we can't compute. So the coefficients of the operators are unknowns to us, because we don't know the high energy theory. The coefficients of the operators are describing the ultraviolet physics. They have the 1 over lambdas in them, if we make them dimensionful. So the couplings or coefficients, I use this language interchangeably, are unknown. And so the procedure we might adopt is we just fit them to experiment. And the power of effective field theory is that we, only have a few operators or a handful of operators, even if we have 10 operators, there's a lot of experimental data out there. And then the coefficients are usually just numbers. So we just fix those numbers, and then we can make predictions for the angular spectrum, or we can make predictions for a different cross-section, add a photon, etc. And so this framework is still very powerful even when we don't know theory one. Okay, but it's sort of a different paradigm. And if you're in a situation where you know theory one, sometimes using this language of bottom up is still useful. You could say, oh, let me not do the calculations from theory one. Let me do this first, get a complete basis of operators. And then I go back and do this sort of theory one to theory two matching, see if I get the same answer, get some intuition about maybe some of the operators we don't find at some order in perturbation theory, others we do find. So it's not like it's either or. You could use both. But if you don't know theory one or it's too complicated, then you're stuck in this paradigm here. Any questions? Okay, well, just to see who's awake this morning, let me ask a question to you. So we have these two paradigms. Can someone give me some example of effective field theories? Not ones we've covered in detail in lecture, because that would be too easy, but some example of a top-down effective field theory. Yeah. Heft. So Heft is a bottom-up effective field theory. So Heft is like SMEFT, where we don't need to do, so it falls in this category. Yeah. But thanks for speaking up, yep. HQET is a top-down, absolutely. You know the QCD Lagrangian, you can match onto heavy quark effect theory. Anyone else for a top-down? Yep. Non-relativistic QCD, yep, very good. Non-relativistic QCD is two heavy quarks. Again, we know the QCD Lagrangian, we can match down onto it from QCD to non-relativistic QCD. Yep. Yep, exactly. Standard model can be matched onto that. How about bottom up? Heft, very good. The standard model effective theory, yeah. Yeah. Chi-PT, yeah. Usually Chi-PT is thought of as a bottom-up effective field theory. We're working in terms of pion fields. We construct it from the bottom up using the known symmetry breaking pattern of how spontaneously the chiral symmetry of QCD is the global symmetry is spontaneously broken. And we use that without reference to exact calculations. And the reason there is because the exact even though we know the mother theory, the matching is too difficult, typically, because the matching would be non-perturbative in that case. It's at the non-perturbative scale. We're interested in very low energy pions, below lambda QCD, if you like, or below the chiral symmetry breaking scale of order of GeV. And so the matching is difficult. You could do the matching, but you'd have to do it non-perturbatively. And in chiral perturbation theory, people do the matching on the lattice. People calculate the Wilson coefficients of chiral perturbation theory using lattice calculations numerically. But it's too difficult for us to do on the blackboard, so it falls in this category. Another example that falls in this bottom-up category is actually quantum gravity. If you think about gravity and you think about it at low energies, you can put in the higher order interactions, and this is a famous paper by 't Hooft and Veltman. It's what 't Hooft was working on when the QCD beta function was discovered, and so he wasn't working on that because he was working on this. Even though people believe that he knew the answer. So quantum gravity is an effective field theory we could think of from the bottom up. We know what the degrees of freedom are, and we could just write down higher dimension operators coupling in gravitons, kind of in a perturbative way of thinking about expanding in 1 over m Planck. And that's a reasonable way of thinking about it. Of course, it's not going to answer all questions, in particular Planck scale questions it cannot answer, but it can answer low energy questions about how gravitons scatter. Yep. String theory would be a theory one that I could then, match onto like, yeah, classical GR or semi-classical GR. Yep. Yeah, exactly. Okay. Good. So the rest of today's lecture, I want to do another example of effective field theory for you. And the reason that I want to cover this example is that it gives you appreciation for the fact that maybe the power counting is not always just simply in dimensions. A little more complicated than that. And so this example is going to be a non-relativistic effective field theory. And in particular, what I'm interested in are short-range interactions. I'll talk a little bit about long-range interactions, but our focus will be on short-range interactions. Short-range interactions in an effective field theory sense means local operators. So we're going to think about non-relativistic particles with short-range interactions. And just to have some physical systems in mind, let me describe a couple. So one thing that falls in this category would be if we were looking at very low energy nucleons. So neutrons and protons, N and P, at very low energy, that the momentum, P, of these protons and neutrons is much less than all other scales I can think about, in particular less than the pion mass, kind of lambda QCD scales like the rho mass or the nucleon mass itself, which is sometimes denoted N. So sometimes we say N is sort of the N and the P. So a very low energy scattering of nucleons would fall in this category of non-relativistic particles, but there's some interactions. Another very interesting system where this effective field theory is going to be useful are cold atoms. So cold atoms, a key system in atomic physics. I'll make a list here of different types of systems. So you could have a Bose-Einstein condensate. You could be studying alkalis like hydrogen, lithium, sodium. You could be studying helium, all at very low energies. So you've cooled the system down to very, very low energies. Let me describe to you how low is low, and it's very low, lower than anything else, and very, very low temperature, very, very low energy in these systems. In some sense, that's perfect for effective field theory, right? If we've got every scale is a high energy scale, and like what's left is just sort of the energy of the particles in the system. So what is low? So mass of the atom, let's just start listing some scales. Well, masses of the atoms would be measured in GeV. Of course, there's the Bohr radius, which we've talked about. It's come up several times. This is in keV. There's the sort of energies of electrons in the atoms, and the energy splittings in sort of Bohr are in units of like tens of eV, or fractions of that. Even the hyperfine splitting, right? So there's hyperfine interactions. These are spin-spin interactions. These are at a scale, these are sort of suppressed in a usual hydrogen atom EFT, but from our point of view in this EFT, this is a high scale. The spin-spin splittings are high. So like this, the one spin state is going to have much, much, much more energy than another spin state. We're going to integrate out, spin up and keep spin down effectively because of this, or not technically up and down, but there'll be some spin singlet and triplet. One of them will have lower energy, and we'll keep the lower energy one. There's vibrational interactions in the system. These are coming about because of the van der Waals force, for example. So these are at 10 to the minus 6 eV. Those are integrated out too. And then we get down to some cold energy scale, which might be 10 to the minus 10. Okay, so all these scales up here are high energy scales that are integrated out, and we expand in them. Okay, so let's think about the effective field theory for this. Well, the first thing is, what are the degrees of freedom? The degrees of freedom, I will call psi as a field. Well, we obviously need a field for the atom or the nucleon. That will be psi. I will kind of describe it generically as either one of these. And then we have psi dagger, and it does the job of creating the nucleon or atom. These will be the main players. I don't have to tell you, like, psi could be a boson or a fermion. I'm using notation that's typical for fermions, but it could be a boson. It's just a notation. Okay, the nucleon's a fermion, but some of these atomic systems like Bose-Einstein condensate, the Bose is because it's bosons. Okay, so that's step one. Step two is thinking about symmetries. Of course, the exact symmetries may depend on the exact problem, but there's some that are sort of fairly generic, and so we can keep kind of not specifying exactly what problem you are dealing with and still sort of impose some symmetries. Well, one symmetry that we have is a U1 symmetry for particle number. This is a symmetry where psi goes to just a phase times psi. And particle number here is preserved because the mass of the particles are very, very heavy. So we can't have pair creation in this problem because there's just not enough energy. There's not enough energy in the system for if we have some atom that's cruising along, it can't split into three because we just don't have enough energy in the system for that to happen. There's no antiparticles, just particles. There's no pair creation, so if we don't start with any antiparticles, then none of them get created. Okay, so we have a particle number conservation from this symmetry. And basically this means that when you're constructing operator, if you want to sort of preserve this symmetry, if you've got a psi, you better have a psi dagger. And that means that you're going to have something, your operator might annihilate something, but then create it again and then preserves the number. Okay, something else that's a good symmetry is rotations. This is a non-relativistic theory, so the Lorentz group is going to be broken, but of course rotations we still have. And that's going to tell us things like if we have some spatial derivatives, that we better dot them into some other thing with a spatial index, like grad squared is rotationally symmetric. Okay, parity and time reversal turn out to be symmetries that we are typically able to impose, so we'll take those for granted as well. And then finally, there's sort of the boost invariance of the Lorentz invariant theories. And in a non-relativistic context, that becomes a Galilean symmetry. So there's a Galilean boost, a non-relativistic boost. Let me call it Galilean symmetry, which is a boost of the system. Okay, I decided to write down for you what that looks like. So you can work out that the way that this acts on psi is by a phase factor. So the boost is described by some parameter that is called v. So velocity, if you like, that you're doing the boost by. And there's sort of a phase, and then a translation, and the translation is only in the spatial coordinates by vt, and the time coordinate is unchanged. And this is the action of the boost on the field psi. And what this symmetry does, which is the descendant of Lorentz symmetry, is it connects some operators. For example, it allows a kinetic term that looks like this. And these terms, the time derivatives and the spatial part, are connected by this Galilean symmetry. So this combination is invariant. And this is sort of the dispersion relation that E is p squared over 2m. It's coming from that operator in the Lagrangian. So if you like, it's it's connecting the energy and momentum by the dispersion relation, protecting it from, receiving quantum corrections, etc. Another thing that's allowed would be spatial derivatives, but spatial derivatives better be kind of witchy way derivatives, which I put this little arrow on, meaning a derivative to the left minus a derivative to the right. And then, the boost will cancel out because in the difference, the VT term will go away. So just having only derivatives on one thing. So differences of momentum are boost invariant, but an individual momentum would not be. Okay. Now this last symmetry here, we kind of have a feeling for the fact that it's an approximate symmetry. We know that because we think, oh, Lorentz invariant must be true of the mother theory, even if I don't know what it is. So symmetry is approximate, and we could think about writing down higher dimension terms that violate it, even if we're not thinking that we're going to violate rotation invariance, not thinking that we're going to violate P and T. This one we might choose to violate at higher orders. Typically people do. But at lowest order in the theory, we think this is a good symmetry to impose, this Galilean symmetry. Okay. How does the power counting work? This is sort of the main reason I wanted to discuss this example. Well, this theory violates one of the properties of the theorem that I described to you, connecting power counting in dimensions. That was Lorentz invariance. This is not a Lorentz invariant theory. Okay, so we have to revisit power counting. And there's a general way of doing that. If we don't know the power counting, then this is the procedure that you go through. What you do is you start with the free theory. Okay, well, we have an idea what the free theory is going to be. This should be the dispersion relation. So the free theory has an action. I'll separate the time integral and the spatial integral. The free theory is going to have an action with this I partial t, grad squared over 2m. That's going to give the dispersion relation for our psi. There could be some corrections, which we'll ignore. Maybe those are relativistic corrections. So maybe there's some higher terms still in the free theory. But this is going to be sort of the lowest order free theory. And then we can think about power counting already just from this free theory. And that's going to determine the power counting of psi, because we're going to normalize things so that this term is leading order. This is our choice. But of course, any other choice would be weird. To have a dispersion relation with a non-canonical normalization would just be strange. So we're choosing to not be strange and normalize this thing canonically, meaning leading order in the power counting here. So we have to go through and power count all the things here, and then we can figure out the power counting of psi by demanding that the action have power counting dimension. It's not really dimension anymore, but power counting order 0. Well, we have to power count t's and x. Power counting t's and x, which are also here, right? Spatial derivatives and time derivatives. That comes about from the power counting of the momenta and energies. And I'll just do the power counting in terms of p. Okay, I can make a choice. So let's count p's. Well, E is p squared over 2m. So E counts like 2 p's. Time counts like 1 over energy. Space counts like 1 over p. So each x gives a 1 over p. Each time gives a 1 over e, which counts like a 1 over p squared. So x is p to the minus 1, t is p to the minus 2. Okay, so let me just write up here, p to the minus 2, p to the minus 1 cubed, so p to the minus 3. So altogether, the action is giving p to the minus 5. Time derivative is an energy, so this is p squared. derivative squared is a momentum squared, so this is p squared. I don't know the power of psi, so let me say it's p to the alpha. And now we can figure out what alpha is by demanding that the sum is 0. Okay, so we add things up. We get p to the 2 alpha, and then 2 minus 5 is 3. So the whole thing is 2 alpha minus 3. And we just choose, as I said, that we want this to be sort of, we have some choice about how we normalize things, and the nice choice is always to make this free action have no power counting, p to the 0 in this context. So alpha is 3/2. And the field psi scales like p to the 3/2. Okay. So we have a power counting. That's time derivatives scale like p squared, spatial derivatives scale like p. So it's not just dimension counting because time and space are treated differently. And psi scales like p to the 3/2. This is our power counting. And now we can go and build operators with more psis and more derivatives, and we know how many p's they have in them. So we're thinking of doing a p over lambda expansion. It's just that when we count the p's, it's not simply dimensions. We have to be, it's like almost the dimensions, right? Of course, if psi is a boson, and maybe, but anyway, we've sort of normalized things. So this is the dimension of psi. So it's close to dimensions, but a little bit different. So we're still doing a p over lambda expansion. And now we can start talking about interactions now that we sort of have a power counting. And I'm interested in short range interactions, meaning interactions that I build out of local products of the field. So I'm interested in something that sort of would interact, say, four of these atoms or nucleons at a point. So it'd be like a psi dagger psi squared operator. So I'll call these two-body interactions. There's two bodies in and two bodies out. Remember, there's particle number conserved. So I can just write down these types of interactions. Often, because there's two in and two out, it's sort of convenient to separate the operator into psi dagger, psi psi. We can start building derivative operators. We need to use these Witchy-way derivatives to have a Galilean invariant, so I'll just stick with sort of imposing Galilean invariance. There could be some subleading operator with momenta that looks like that. There's another one that we could write down, which I'll call CT prime, where both the derivatives dotted into each other act in the same bracket. And this is, of course, plus Hermitian conjugate. And then we can keep going. 4 derivatives, etc. Always an even number of derivatives, just to dot the spatial indices together. So these are contact interactions, short-range interactions. They're called two-body because we have 4 psis. We haven't gone to higher numbers of psis, we've just gone to higher number of derivatives. The series goes on forever in the number of derivatives. Okay, let me call the operators here O. So we have integral d4x, time and space, of O0. We don't know the C0, we want to sort of figure out what this power counting for this C0 is, or sort of what the dimensions, how things are working. So let's think about d4x for O0. Well, this is p to the minus 5. And we look at the psi dagger psi all squared. Each of the psi's is 3/2. 3/2 to the 4th power is 6. So this is p. So therefore, C0 will go like 1 over lambda. It's a p over lambda expansion, so we expect that there's a lambda inside the C0. integral d4x O2. Same thing, p to the minus 5. Now there's two extra derivatives, so this becomes p to the 8. So this is p cubed. So C2 should have a 1 over lambda cubed. Kind of get the p over lambda expansion. And if you look a little bit at what's going on here, and you think, well, okay, you think a 4 fermion operator in the relativistic context, that was always had a coefficient of dimension -2. So this is somehow weird, right? I've got a non-relativistic context, 4 fermion operator, and I go through this counting and I find a lambda. It should be mass dimension -2, but sort of the number of lambdas is only 1. Remember that lambda could be any of these low energy scales. It could be like the hyperfine splitting or something, right? What's making up the rest? So the power counting is not in mass dimension. It's in these p's, and this p over lambda expansion. I've determined the lambdas. I haven't worked out the mass dimension of the c's. Something's a little off. I have to think a little bit to get the mass dimension of the c's. A little harder. So the mass dimension of the C0 is -2, and I've only sort of figured out one of the factors that comes into it. And the other factors are actually masses of the particles, of the nucleons or atom. And I could be a little more careful about the counting and count those masses too. So when I power counted the T, I said, oh, T is P -2, but somehow the dimensions there are off, right? And the thing that's making it up is that there's an M. E is P squared over M, so I better count those M's. And so we can do a counting of the M's. So T was M over P squared. And so in terms of the M, each T counts like an M. P doesn't count like an M. I'll denote that by M to the power 0, no M. Time derivatives have M inverse. Spatial derivatives have no M. So there's very quickly the counting for the M's. This term and this term have the same M counting, both M -1, as sort of had to be the case. And if you go through this procedure, you see that in this contact interaction, you have an M here, no M's there. The fields don't have any M's. You can go through the leading action, and in the leading action, over here, we have an M, and we have a 1 over M. So those balance, and the psi's don't need any M's. So psi M to the 0 from the pre-action. And then we go over here. Now we don't have the time derivative. There's an M from here, but it has to be balanced, and the thing that balances is the C0. So the C0 and the C2, they all go like 1 over M. All the CI's go like 1 over M. And that's making up for the mass dimensions. I can put that in here, and now the mass dimensions are sort of correct. Each one of these has a 1 over M. And the presence of the M is kind of a normalization choice, is sort of the natural one in the effective field theory context. But it's actually, as we'll see, making the scattering M independent. Having coefficients that go like 1 over M is actually giving us a good M goes to infinity limit when we think about non-relativistic scattering, just because there's an extra M in some prefactor somewhere, so you need this sort of 1 over M to cancel it. And we'll see how that happens a little later on in this example. Okay, so this is how it works. It's a little bit different than, a little bit more complicated than the relativistic theory, but not that much more complicated. We have a not pure dimension counting, but it's close to dimension counting. There's 2 dimensions here, M and lambda, but we could work them out pretty quickly. So not really that hard. Let me make a comment about the different theories that I mentioned at the beginning, because the different, sort of described it so far very generically, but the different theories do actually have some implications for which operators survive in that series there I wrote. So there's quantum numbers, and depending on those quantum numbers, some of the operators could be ruled out. So some interactions may be absent. So for example, if I only have one species of fermion, like, there's two spins, but one of them is heavy and I integrated it out, so I'm left with only one species of fermion, then I can't write psi, because those are the same operators. Fermion's anti-commute, so there's a minus sign. And so this vanishes for fermion for one species of fermion, one spin state. So if we have a system with only one species, we could have a derivative. The derivative distinguishes the two psi's. If I had a derivative in between, an operator like psi, Witchy-way derivative psi, this is okay because the derivative has a minus sign too, and it compensates when I flip the fermions. So that would be fine, but the first one not. The second one is actually a problem for bosons, because if I have bosons, then the psi's commute, and the derivative doesn't, so this is going to vanish for bosons. Okay, so in general, there's some constraints on the operators that is related to, again, if there's only one spin state, like a scalar boson that is related to the quantum numbers. In the case of the nucleon, it's kind of interesting. In the case of the nucleon, when I think about psi, there's both spin and isospin, and those things are symmetries in the effective theory. And so we can classify in some kind of spectroscopic notation that you may remember from a quantum mechanics course with the spin, the angular momentum, and the total angular momentum. We can classify the allowed states of psi as two. We either have a spin triplet or a spin singlet, and then in the S wave, it would be these two. Of course, there's higher waves as well, P wave, D wave, but the lowest two are the S wave. And then there's isospin. So there's spin and isospin. Isospin is usually denoted by I. And to get the overall spin statistics theorem for fermions, where they anti-commute, to get that right, you kind of have a connection between the spin and the isospin. So if you're in the isospin, if you're in the spin singlet, you need to be in the isospin triplet. If you're in the spin triplet, you need to be in the isospin singlet. So those two come together, and you could go on. Okay, but this is just about counting quantum numbers. So this means that in the sort of S-wave scattering, these types of operators that I wrote down would actually be S-wave scattering. This would be like a P-wave scattering, actually. The extra momentum is putting it into a P-wave. This is sort of a term that has both D-wave and S-wave. And in classifying things, you sort of have two S-waves in the nucleon case, whereas in some other case, you might only have one. Okay. So that's a little detail that where the exact theory we're talking about comes in. Let's keep going. What about three-body? Three-body short range. This would be an interaction where three things happen. Three things come in, three things go out. Let's do some power counting. I'll call the coefficient D0. I just have three psi daggers, so psi dagger psi cubed. Well, this is p to the 9. This is still p to the minus 5. So overall, I get p to the 4. So the D0 is going to want to have a 1 over lambda to the 4. This is matching it. There's going to be that 1 over m. And that's the right answer for the D0. Okay. So we sort of see that all short distance interactions are small. They're all suppressed by at least 1 power of lambda, and the three-body are even more suppressed. They're suppressed by 4, which may be intuitive. There's less chance of three things hitting each other at a point than there is the two things hitting each other at a point. Okay, what about long-range forces? These are all, I've described to you here short-range forces. Okay, in nature, there are things that are long-range, like Coulomb interaction. photons propagate and give long-range forces. It would be remiss if I didn't discuss a little bit the long-range forces, so let's spend a few minutes on that. And just show you that we can use power counting techniques also for long-range forces. Let me pause actually just to see if there's any questions about the short range before I go on to long range. How would a long range force look, right? A long range force means, like, if I was thinking about 2 to 2, there's some kind of interaction that's extensive between the two particles. Maybe it's a Coulomb type force, maybe these particles are charged. And we could do this, set this up in different ways. This thing that's exchanged is typically off-shell in the non-relativistic sense. It's not an on-shell propagating particle. It's like some kind of potential. That's how we'd usually describe it in quantum mechanics. In the field theory, that would be an auxiliary field, and we could put in some auxiliary fields and describe this by local interaction, some kind of propagator for the auxiliary field and a local interaction. Let me do it as kind of a shortcut and say I integrate out the auxiliary field. Then the long range LR action would look local in time, but it would look non-local in space. And so it would look like this. It would look like psi dagger psi at x, where x is time and x. There would be some potential that I would get, which would usually depend on only the difference between x and x prime, if it was, for example, a Coulomb. And then there'd be a psi dagger psi at x prime, where x prime is at the same time, local in time, but non-local in space. So this is t comma x vector, and this is t comma x prime vector. So this is the kind of thing that I would get from integrating out the auxiliary field. I get some potential. And we can go through our power counting for this type of operator. Well, we have psi dagger psi. We know how that power counts. We have this, and we know how that power counts. So there's p to the minus 2, p to the minus 3, another p to the minus 3, so overall p to the minus 8. Each of these gives a p cubed. Okay, so we have 6 minus 8, it's minus 2. And then there's the potential, and I didn't tell you what the potential is. So there's some potential that has a p power counting. So this square bracket with a subscript p means the p power counting of v. This is a notation. So not the dimension, but the p power counting. So if I pick a v, then I can tell you the answer, but if I try to be generic, then that's as far as I can get. So let's pick a v. Let's do Coulomb. So Coulomb v is alpha over r. R scales like 1 over p, so the v scales like p. So now I know the scaling of the v under the p, and the long-range force goes like 1 over p. If I count the m's, there's an m, because the action's in dimensionless, so it's m. There's an m from the time, so it's m p minus 1. And there's also an alpha, so let me put that in. So it's m over p alpha, and people often write that, they sort of define that as alpha over v, v being some kind of relative velocity of the scattering. Okay, so if the velocity in the system, which is p over m, is of order alpha, and you're thinking about charged particles, then this long-range force is important. But it's only important if the particles are charged. So if the particles are neutral, you don't have this Coulomb force, right? And when we have a Bose-Einstein constate or any of these cold atom systems, we're always thinking about neutral. Okay, we don't want Coulombic effects, which just blow everything out of the water and we wouldn't be able to cool. Okay, so we're really doing it for neutral particles, and then we don't have Coulomb. In the neutral particle case, you could still have a dipole moment for your atom, right? So you have a dipole-dipole interaction. That's the van der Waals force. For neutral atoms. And in some quantum mechanics course, maybe an advanced quantum mechanics course, you might have worked out what that looks like. You're doing some expansion. It's a 1 over r to the 6 potential. So it scales like p to the 6. Kind of small from the point of view of our power counting. Up here, to get the action for this long-range force, we subtract 2. There's still an m. So it's m p to the 4 times c6. And therefore, we can determine that m times c6 goes like 1 over lambda to the 4, where lambda would be some scale characteristic of the dipole of the atom related to the van der Waals. Okay, c6 goes like 1 over m lambda to the 4. So there's the power counting for the van der Waals. So again, it's a suppressed interaction, powers of lambda downstairs. Can treat it, it comes in. At p to the 4, we have to include it. Up to p to the 4, we don't. So long-range interactions, no real problem. Okay, I'll go for maybe 5 more minutes and then we'll break for questions. So any questions about long-range forces? I could have gone through things with auxiliary fields. It would just take me longer, so I didn't. Okay, so this is interesting effective field theory. We have interactions, they're perturbative. We can do some calculations, make some predictions. When I wrote down this effective theory, I'll just make this as a kind of an aside as I erase. When I wrote down this effective theory, when I wrote down the higher order short distance interactions, I only wrote spatial derivatives. I didn't write higher order terms with time derivatives. And that's again because I have in the back of my mind that if I had a time derivative, I could make some field redefinition and get rid of it because the leading order action had a time derivative plus a spatial derivative squared over 2m. And if I use that, I can get rid of any time derivatives in the higher order terms. So I don't need to consider higher order terms with time derivatives. So just a little note. So we are using that freedom. And that's actually a very nice thing to do because, okay, it also makes calculations a lot easier. But I've done it in the background for you. This theory is actually particularly simple. So we're just going to carry out some loop calculations in this theory, and I can do them on the blackboard with keeping all the factors. So let's do some loops and see. We haven't talked very much about loops. I'm going to talk about loops in more detail tomorrow in lecture and get into some of the subtleties. But today, non-relativistic theory, loops very easy. In particular, there's no kind of loop if I just take 2 of these contact interactions, there's no kind of loop like this. A loop like this would have a particle and an antiparticle in the loop. And there are no antiparticles. So if you just try to put 2 particles in, you find this loop is 0. So the type of loops that exist are loops that look like this, not that look like that. And maybe once I write this one down, we can see why that one would be 0. So let's look at the loop like this. External energies and momenta, center of mass frame, so same energy, back-to-back momenta, so EP, E minus P, goes to E P prime, E minus P prime. P prime is a different angle than P, same magnitude actually. This is a loop that carries energy. There's no momenta flowing in. And of course, there's some loop momenta that I'll call Q. And if q goes forward through this one, it better go backwards through this one so that it's gone when it gets to there. Q is both an energy and a momentum. It's a 4-vector. So I write E plus Q in a little bit of abusive notation, but Q is a full 4-vector with Q0 and Q vector. And so then I can think about calculating this Feynman diagram. Let's calculate it for the simplest possible thing. So I'll put in C0, C0, two of those contact interactions. Contact interactions, this is like lambda phi 4 theory. So there's some coupling, minus IC0. I can normalize things, so it's simply that, minus IC0 squared. That's the coupling. And then I have a loop integral to do. I'll do the loop integral in dimensional regularization. So I have an integral d dq, and then I have just two propagators here. And they're non-relativistic propagators. So here's how they look. Energy has an E component plus a Q0 component, and then minus 3-vector momentum squared. Okay, there's a plus I0, it's a propagator. And the other propagator is E minus Q0, and then minus Q vector squared over 2m plus I0. And there's another I upstairs. The little slash on the D means that I divide by 2 pi. So D slash Q in D dimensions is D dq divided by 2 pi to the D. This is just a shorthand. Keep track of those 2 pi's. So in dimensional regularization, which I often use with D equal to 4 minus 2 epsilon, I can regulate divergences, do loop integrals. And this is how this loop integral would look. In the non-relativistic context, the Q0 and the Q vector are not like together, right? They're like separated. So it's the way that you often do these integrals is you just do the Q0 by contours. And this is a particularly easy integral to do by contours because there's only 2 poles and one is above and one is below, and the contour converges at infinity, so we just do it. So close above, for example. And then the i's cancel. There's minus I squared times I, so there is no I. I do the contour, I close above, I get an I. There was a 2 pi in the dq0 over 2 pi. That cancels in the residue theorem. Leaves behind an I, so that's where this I comes from. And I can write the answer as now just a spatial integral. And it's convenient to sort of rearrange it into something that looks like a familiar integral. So I can multiply by m on the top and bottom, and then I just have a q squared minus me minus I0, which looks like a standard relativistic integral that we know how to do, where now the n here is d minus 1, so it's 3 minus 2 epsilon. So I just look up that integral, the back of some quantum field theory textbook. And it's some gamma function, 1 minus n over 2. Looks like this. And then I want to expand around epsilon equals 0. And when I expand around epsilon equals 0, I just get an answer. There's no problem. This is 1 minus 3 halves, gamma minus half. That's just some number. Involves a root pi. This thing goes to something finite. So going to epsilon equals 0 and not thinking about any kind of divergences, which is effectively using the MS bar scheme. There's no divergences to subtract, so we don't kind of make any finite subtractions. That's MS bar. We could just take and evaluate this. There's a 1 over 4 pi. And then there's this factor, which is now a square root. And 2me is just p squared, right? E was p squared over 2m, so 2me is just p squared. And p squared and p prime squared are the same. The magnitude's the same, the angle is different. So this is just a minus p squared minus I0 to a square root. That's like you're down below the contour, just below the cut. So it's minus IP. So this is minus IC0 squared. and then there's a minus IP, and then you can decide where you want to put the m over 4 pi, but let me put it there. So it's a very simple answer for this loop integral. Okay. So I want to go a little bit further with this example, but I'm going to stop here because we're at a good time to stop, take questions. I'll tell you just in words where we're going to go with this. It turns out that the loop calculations in this theory are so easy, I don't have to just stop with this one. I can actually do for you a loop interaction involving any number of derivatives, and I can carry out the loop integral just as easily as we did this one. And I actually don't have to stop with one loop. I can do 2 loops, 3 loops, 4 loops, because of the fact that the topology of the loops just remains kind of iterative. It's no harder to go to higher order. So in this theory, I can actually just calculate under some approximation that I'm neglecting relativistic corrections what the higher order contact interactions do. And I'll just show you how that works because it'll give us some feeling for some of the tricks of dimensional regularization. And it'll be a good segue next time into sort of discussing more formally some of the issues associated to loop calculations and how matching calculations work. So that's kind of where we're going with this. But let me stop there, take questions. I'll prompt questions by saying, if you look at this calculation here, there's kind of like some wool that's been pulled over your eyes if you think about what's happened, which I'll talk about next time, but if somebody notices, I'm happy to talk about this time. Yep. Oh, good. Yeah, I didn't say. So I meant to say. So if you look at this graph here, what would happen is one of these I0s would become a minus I0. And then the poles are on the same side. You evaluate, you get 0. And that's effectively saying that you need an antiparticle. But this propagator is only allowing particles. You only have particles in the theory. It's not like a relativistic theory where there's 2 poles, one for the propagate, one for the particle, one for the antiparticle. In this non-relativistic theory, there's only one pole in the energy. That pole corresponds to the particle, not the antiparticle. Yep. Thanks for asking. Yep. Yeah. Yeah. Yep. Normalize correct, like if you saw like that there was a 1 over 90, right? And so there can be some suppression from that, but like with some understanding of the numerical factors, order 1. Yep. Yeah. So like you can try to count as the factors as best you can as far as tracking like numerical factors, right? So could I have guessed the 1 over 90? Well, I would have guessed maybe that it could be suppressed by something, but I probably wouldn't have guessed it'd be suppressed by 1 over 90 if I was just to guess, right, in the Euler-Heisenberg. In general, you can try to come up with methods of guessing large numerical factors in dimensionless quantities. There's one set of such things that you can figure out, and that is 4 pi's. So you can do a power counting for 4 pi's, and you can track where all the 2 pi's, 4 pi's are showing up in your quantum field theory. And since 4 pi is 12, it's a pretty big number, and if you've got 4 pi cubed, that's a pretty important thing to track. But that you can do with power counting techniques. But tracking just like 2, no, I can't do that. Yeah. Good question. You can get logs. They're less common than in relativistic theories, and you see that in this calculation you didn't get a log. if you look very carefully, this was actually what I was hinting at. This is d3q, and there's q squared. So it's like d3q over q squared. It's actually power law divergent, linearly power law divergent, not log divergent. And in dimensional regularization in the MS bar scheme, I don't see a power law divergence. They're just eliminated, set to 0, and I just get a finite answer. That was the subtlety. Yes, but there's no logs. But you know, in some higher loop diagram, I could get a log. It just doesn't happen yet. You need to, yeah, you need to go to a slightly more complicated case, but then you can get logs.